artificial intelligence, very appropriate. So her two truths and a lie. One fact about her, she claims, is that she hates cilantro. Another fact she claims is that her dog is a potato. The third fact about her is that she wanted to be a fashion designer growing up. So again, by general noise making and applause, how many of you think the first fact is a lie? Pretty good. How about the second fact? And she'll explain it later if it's true. And the third fact, how many people think the third fact is a lie? All right, Anne, which is it?
The first one is a lie.
And everyone's question is immediately, what with number two?
My dog's name is Spud, so he's a potato.
All right, let's also welcome to the stage our second speaker, Aimee Schechter, or Aimee Schechter. We've been saying no relation with her name, which is the Schechter function, no relation, because there's a famous function in astronomy called the Schechter function. So her two truths and a lie are, one, when I was 5, I wanted to be an astronaut when I grew up. 2, I studied abroad in Spain my junior year. And 3, until I published my research note, my greatest accomplishment was having my name on NLB.com. Through the same noise-making system, how many of you think 1 is the lie? How many of you think 2 is the lie? How many of you think 3 is the lie? And
Yeah, number 2 is the lie. I studied abroad in England my sophomore year.
is the audience 3 for 3 so far? Rebecca and I thought these were really good. We were like, wow, some of these are very hard.
It's because all our friends are here. They're screwing with it.
All right, we are going to hear from these two amazing speakers, artificial intelligence and the Schechter function, no relation. Give them a round of applause.
All right, hi. So I'm Aimee Schechter.
And I'm Dattilo.
And we're new astronomers.
Sorry, I missed it.
You missed it.
I missed it, I'm sorry.
And okay, so as undergrads, we both accomplished some research, we're both published, but we also do really remember what learning a lot of these things was like for the very first time.
And so we're going to tell you some strange things about astronomy. So as astronomers, we look at objects in the sky, and we measure properties about them. And one of these properties is how bright these objects are. We measure this with a system called magnitudes, and there are 2 types of magnitudes, absolute magnitude and apparent magnitude.
So absolute magnitude refers to intrinsically how bright that star is. So you can imagine that if we're here on Earth and you see a bright star that's very, very far away, it might look similar to a dimmer star that's much closer to us. But we want a way to measure stars kind of uniformly. And so we use this absolute magnitude system, imagining that all stars are at the same distance of 10 parsecs. We'll get to parsecs in a minute. And that's how we define their absolute magnitude.
An apparent magnitude is really just how bright that star appears to us here on Earth. And so, for example, the apparent magnitude of the sun is minus 26.7, which doesn't really make sense because it's the brightest object in our sky.
So it seems a little bit ridiculous that this bright object would have the most negative magnitude. It's very counterintuitive, but this system came from a few thousand years ago. A Greek astronomer named Hipparchus looked up at the stars in the sky that he could see with his eye, and he basically said, I'm going to call all of the super bright stars 1, and then he ranked their brightnesses going down all the way to the faintest things he could see at number 6. Of course, now we can see fainter things than he could with just his eye thousands of years ago.
So now we have a magnitude scale ranging from 1 for those really bright things in that picture to the mid-20s or even down to 30 for extremely faint, really far away galaxies. So we can plot these objects on this diagram called the HR diagram.
So this diagram is really helpful for astronomers. It's a way for us to look at stars and their temperature and their luminosity and their radius and look how they evolve over time. So we really like it. But if you take a closer look at this diagram, you'll notice that there are some letters on the bottom, and those letters are in a complete nonsense order, not alphabetical at all. And if you look below the letters, you'll see the numbers referring to the temperature of all of these stars. And counterintuitively, the temperature gets smaller as you move to the right.
So this is quite silly, but it's because of a woman called Annie Jump Cannon. About 100 years ago, she was a Harvard computer, and she sorted stars based on their spectral lines into many different categories and gave them these labels alphabetically. After she did that, people realized that these categories aligned with temperature, but they weren't in the same alphabetical order of these spectral classes, and so that's why we have this jumbled up, mixed up x-axis on the HR diagram. We also use terrible units in astronomy, like the parsec and the light year.
So both of these, yeah, that's me. Both of these sound like they should be times, but they are distances, often misused in pop culture. So if you're wondering what a parsec is, this unit of distance that astronomers love so much, first we have to establish angles on the sky, and so you're all gonna look silly, but the best way to do this is if you hold out your finger straight in front of you, and then look at your finger with one eye closed, and then switch which eye is closed, and keep going back and forth. And you'll notice that your finger appears to move with respect to the background of the room. And this same thing happens with stars with respect to their background stars as the Earth moves around the sun. So this is my little diagram of a parsec. So the sun is there in the middle, and then the two blue dots are Earth at different points in the year going around the sun. And we define the distance between the sun and Earth as 1 astronomical unit. And we say that if the base of that triangle is 1 AU, and we are looking at a star that has moved 1 arcsecond, so 1/3600th of a degree on the sky, then the distance to that star is 1 parsec. And while this might seem like a complicated system of measurement that we want to use, we really like it because if you do 1 over an angle that's in arcseconds, it automatically pops out a distance in parsecs. We do love it, you're right.
The light year is also not a time, it's a distance, and it's called that because a photon, a light particle, moves at the same speed always in a vacuum. And so a light year is the distance that it moves in 1 year.
So that is like if you were going 60 miles an hour and you told me that you were traveling at 60 miles an hour for an hour, but then never said the actual distance that you traveled. Just that's your distance.
In astronomy, we also use dumb base units, which are the centimeters, gram, and seconds. So a centimeter is about the width of your pinky, and we use that to measure extremely long distances, like a parsec. A second, we all know what a second is, and we use this to measure years, billions of years for stellar lifetimes. And we use grams to measure how big stars are. And so this is 1 gram of salt, and you should all know that it was extremely difficult to find this picture. It turns out when you type how much is a gram into Google Images, you get pictures of drugs. I didn't expect that. But to give you some intuition for how crazy these units are, I'll give you some references that I have used in multiple classes. So 1 parsec, what we talked about before, is 3 times 10 to the 18 centimeters. That is 3 million centimeters. 1 billion years, the lifetime of our sun on the main sequence, is 3 times 10 to the 17 seconds. 100,000 million seconds. And the mass of the sun, how large our sun is 2 times 10 to the 33 grams. That is 2,000 million grams. And it's absurd that we use units like these constantly to measure our things in astronomy.
But the best part of using CGS as your base units is that the unit of energy in this system is called an erg. And if that's not the best name for a unit you've ever heard, I don't know what is. The first time I came across this unit was my very first research project when I was a freshman at UT, and I was running a simulation of a 20 solar mass star and its death in a big supernova, the big explosion at the end of its life. And I was told, oh, just expect your result to be something on the order of 10 to the 51 ergs. And I was like, what? Because 10 to the 51 is a very hard number to even comprehend. And why are we measuring this in a unit called an erg that I've never heard of before?
So I learned ergs to be 1 erg is the amount of work that a caterpillar does in 1 push-up. And that's how we're measuring supernovas.
So that makes sense.
But the reason why we use these is mainly historical. In the past 100 years, all of the big calculations, the seminal papers in astronomy and astrophysics have been using these units. They also make Maxwell's equations, the fundamental equations that describe electricity and magnetism, they make them slightly easier.
So another number that astronomers are very, very interested in measuring at the moment is H0, or the Hubble Constant. This is a number that describes the expansion of the universe. It describes the age of the universe, very important for cosmology. And then when you look at the units of it, it's in kilometers per second per megaparsecs. So in units you might be more familiar with, that's like me telling you feet per year per mile, because that makes sense as a number. And I remember the first time I read that, I was like, how do you even think about this number? But it turns out that if you do 1 over the Hubble constant, it gives you the age of the universe. And if you plot the speed at which galaxies are moving away from our own on the y-axis and the distance to those galaxies on the x-axis, you get a really nice plot with it's a straight line, and the slope is the Hubble constant. So just don't think about the units too much, and it's an incredible number for cosmologists.
Astronomers are notoriously bad at naming things, including telescopes.
So historically, telescopes have been named after people, after famous astronomers, people who donated money, explorers. For example, at our own McDonald Observatory out in West Texas, we have the Otto Struve telescope, the Harlan J. Smith telescope, and the Hobby Eberly telescope. Sometimes we refer to them as the 2.1 or 2.7 meter. But the people they're named after in diameters seem like pretty reasonable ways to refer to telescopes. But as our telescopes have gotten bigger, the names have gotten a little bit sillier.
Like the Very Large Telescope.
And if you need to do some radio astronomy, we also have the Very Large Array.
And we have the South African Large Telescope.
We already had the Magellan telescopes, so when we were starting to build a new one, we decided to call it the Giant Magellan Telescope. It's bigger.
And we have the European Extremely Large Telescope.
And then lastly, the biggest telescope planned was the Overwhelmingly Large Telescope. But unfortunately, you won't be overwhelmed because this has been canceled. But you can see the cars at the bottom for reference on how big this telescope was supposed to be.
Astronomers are also terrible and love to create acronyms. We create so many terrible acronyms that there are multiple worst acronym lists in astronomy.
So I put together a list of a few of my favorite acronyms that I could find in some categories. So first we have the food category. Since we're in Austin, I had to give a shout out to avocado for a virtual observatory census to address dwarf origins. An egg for evaporating gaseous globule is pretty funny. But both of these acronyms play by the rules. The first letter of all the words is what makes up the acronym. They make sense. We move on to some good pop culture characters. We have Batman and Gandalf for the badass transit model calculation and gas and absorption line fitting algorithm. These are great. They still mostly play by the rules. We're starting to cheat a little bit with calculation and using the whole word of and, but I'll let them slide. And then some of my other favorites that I've found. We have mascara for the multi-site all-sky camera. Camera is definitely cheating on that acronym. There was a conference called Sugar Rush in Shanghai last year. And then we have Michelle for the mid-infrared Echelle spectrograph. I don't think for an acronym you can use almost the whole word of Echelle and then nothing from spectrograph, but you know, that's the acronym. But the best/worst acronym I could find reminded me of this SpongeBob meme called Vestolly, and it stands for Unveil the Darkness of the Galactic Bulge because, of course it does. The only letter that is from the first letter of a word is the capital T of the second the. And I Googled this to figure out what Vestolly even was, because I don't know unless I'm just like really missing something. And it turns out it's an Italian opera that's in French, and this is an Italian collaboration. So I'm pretty sure that's what they named it after. But I think this is really stretching the acronym in astronomy just a little bit.
But it's okay, because this past April 1st, someone came out with an algorithm to help us with our acronyms called Acronym Creation for you and me. And I downloaded this code to try and help me come up with an acronym for my original name for this talk. And we came up with dubious, dumb things about astronomy.
So we hope you guys enjoy learning all about the dumb things about astronomy that we love so much, and thank you for listening to this dubious talk.
There's so many acronyms I want to share with everyone, but like it's just that's a whole tangent we don't need. All right, any questions from the audience? Right here in front.
Oh. Yeah, I'm a really big Red Sox fan. I'm from Boston, and when I was like 11, I entered to be a Kid Nation captain for the Red Sox, and I won the contest. I was one of 12, and so they gave me like a personalized jersey, and we got to represent the Red Sox at charity events and stuff, and we were introduced before a game, and you can go look it up, Aimee Schechter, Kid Nation captain. There I am, 12 years old, like at Fenway Park. It was awesome.
Okay, that was somebody's Twitter question, so come get your keychain anyway. All right, we have another Twitter question. So do you think that the units in astronomy would be less weird had the metric system be introduced to the US earlier on?
They're just too small.
Yeah, I mean, I think they might feel slightly more intuitive, but like CGS, just on that scale, to us makes no sense. And I know that we do have units that are on bigger scales that we use sometimes.
You guys, most of the time we measure things relative to the sun.
Yeah.
And that's quite large, so. But galaxies on the scale of a sun are how many solar masses?
Like 10 to the 11 or
10 to the
something?
11 suns in a galaxy. We tried to make bigger units and it just wasn't big enough, so. Any more questions? Anybody up top that I can't see? Who's whistling? Where are you? Oh, over there.
I also have a question about units, which is, I know you said it makes math simpler, but do you think it has the effect of helping some of us peons who don't understand those big numbers? Because I don't know what a light year is, but I damn sure know what a second is.
Yeah, I think honestly, a lot of the CGS might be an ego thing, because when you hear the sun is 2 times 10 to the 33 grams, you're like, dang, astronomy uses huge things. You learn about huge things.
It does put things into perspective, I suppose. But you're not peons, you're here. You're above peons. Sitting down somewhere over here. Yes, you.
How did you come across the measurement of what an earthworm can do?
It's literally on the Wikipedia page for ERG. It's like the last line in the first blurb. It says Alex Filipenko at Berkeley. That's what he uses in his class. And it does put it on a scale that we can all understand.
So wait, so Berkeley, did you take that class?
I did.
Oh. So you're part of the problem. All right, one more question. Here in front.
Do you think that the guy who set up that original scale, the 1 to 6, was foreseeing that there might be better technology in the future?
Probably not, because I think repeating the question. So he asked if Hipparchus, who looked up at the sky and made the magnitude scale going 1 to 6, saw better technology coming. And honestly, I want to say no, because the system doesn't really make sense when you're measuring bright things in negative magnitudes and, I don't know, really dim things. I don't know. To me, it just seems very counterintuitive, and I feel like if he had some foresight, we wouldn't be measuring the sun at -26, but that's just my personal opinion.
As a person who deals in infrared astronomy, I agree. Magnitudes, as in how things appear to my eyes, in infrared makes 0 sense, since I can't see infrared light, so whatever. All right, so let's thank our speakers one more time.